Decadal Variations in the Global Atmospheric Land Temperatures by Daniel Fralin and Justin Gabbard. To begin, our group organized this presentation to mimic the same pattern in which our paper was organized. I, Daniel, was responsible for collecting the information regarding the introduction to our topic, explaining decadal variations and its purpose in our assigned paper, and the difference in correlation analysis that was done in the study. In addition, I was tasked with narrating this presentation, although all subjects that were assigned to Justin, which include correlation map, spectral analysis, and discussion, were researched and scripted by Justin. The study done by the Berkeley Earth Surface Temperature Group was focused on the analysis of the average land temperature of the Earth to ascertain whether it could be an indicator of climate change. Their data set consisted of 2,000 randomly selected temperature monitoring sites that were not already being used in datasets compiled by the National Oceanic and Atmospheric Administration, the NASA Goddard Institute for Space Studies, the Hadley Centre of the UK Meteorological Office with the Climate Research Unit of East Anglia, and no adjustments were made to the dataset regarding effects such as urban heat islands, which is the phenomenon where urban areas are much hotter than their nearby rural areas due to human activities or instrument changes. The result of their collaborative effort was a broad trend of global warming with minor fluctuations. The group used the data provided by several global climate variability indices to compare their own data against. These data sets include the El Niño Southern Oscillation, ENSO, which is a reflection of the variability of sea surface temperatures in the equatorial Pacific, the Atlantic Multi-Decadal Oscillation, AMO, which is derived from the sea surface temperature records, and the Pacific Decadal Oscillation, PDO, which is derived from the temperatures of the North Pacific Sea. The North Atlantic Oscillation and the Atlantic Oscillation are both different from the other three, as they are both derived from the surface pressure differences at the Northern Atlantic and Arctic. The group's analysis was based on monthly land surface average temperature readings. The data provided by NOAA, GISS, and HAD-CREW was smoothed into a 12-month running average to remove monthly changes. This process is evident to the graph on the right, where the unadjusted data is highlighted in blue, with the smooth 12-month data in black. Data before 1950 was removed from the sample due to the smaller amount of instrumentation stations that existed to collect data. The lack of stations to collect data resulted in the overall results collected by the various agencies to be noisier, and was for this reason excluded. Data was then subjected to a pre-whitening process to remove a large signal that was not being used in order to reduce the overall bias in the study. The procedure effectively removes slow changes as global warming and the about 70-year cycle of the AMO and gives each record zero mean. The root mean square difference between the temperature average and the AMO and the ENSO indices were taken, and the overall AMO fluctuations match temperature variations better than the ENSO index. The table on the right shows the calculated root mean square differences, and the AMO has the lowest with a root mean square difference of 0.75, which compared to the ENSO, which has a root mean square difference of 1.14. The following graphs show the aforementioned relationships. Graph A shows the correlation of the NOAA, GISS, HAD-CREW, and Berkeley Earth temperature averages. Graph B and C use the temperature average of these four data sets. Upon inspection of Graph B, it is apparent to the eye that the temperature averages match very closely to the AMO, and in Graph C, the difference between the temperature average and the ENSO is visibly apparent. Graph D is present to show the similarities and differences between the AMO and the ENSO indexes. This image shows the decadal correlations of the AMO and ENSO surface temperature maps with the NOAA Global Temperature Anomaly map. For the purposes of this paper, only the land surface temperatures are used in the correlation analysis. This map, however, includes both land and ocean surface temperatures because of the strong correlation between the AMO and Atlantic temperatures, and the ENSO and equatorial Pacific and Indian Ocean temperatures. On the land, the AMO mostly affects Africa, Southern Asia, and Canada. The ENSO correlates strongly to most of the continents in the southern hemisphere. As previously mentioned, the ENSO does show a weak correlation to the Atlantic. The variations in the Caribbean are also affected more by the AMO as opposed to the ENSO. These variations are related to the hurricane intensities that affect the southern coast of the United States. Compared to the AMO temperature map, the ENSO is much more intense and complex effect locally. Because of this correlation pattern, the simpler AMO map corresponds to a clear imprint on the large-scale average surface temperatures. These graphs show the spectral power estimates for the AMO and PDO indices, respectively. These graphs are considered periodograms. These are calculated using a Fourier transform with no taper and are designed to yield intermediate frequencies. No error bars are placed on the plot of the AMO spectrum because the expected distribution for a power spectrum is exponential, not Gaussian. Instead, an estimate of the statistical significance of the peak that appears at a frequency of 0.11 cycles per year was developed using the Monte Carlo method. The 9.1-year peak in the AMO may have high statistical significance, but it only contains 30% of the observed spectral power. Because of this, the peak is not clearly present to the naked eye in Figure 1 and Figure 2. Figure 1 shows the decadal fluctuations in surface land temperature estimates and in oceanic indices. Graph A indicates the four estimates of the Earth land surface temperatures given by the NASA, NASA GISS, Hadley crew, and Berkeley Earth groups. Graph B shows a comparison between the average of those four estimates and the AMO land temperature estimate. Figure 2 shows the decadal correlations of the Berkeley Earth land temperature estimates, T average, with the AMO index, graph A, and the PDO index, graph B. Note that the AMO index has the strongest correlation observed. The similarities between the decadal fluctuations and land surface temperature data provided by the different sources indicate that the fluctuations are physical and not the effects of statistical fluctuations. Given that short-term fluctuations such as the temperature rise in 1998 were caused by strong El Niño events, the AMO is still more closely associated with variability in the average land surface temperatures than the ENSO. In the decadal region that was studied, there was only one statistically significant spectral peak, with a period of about 9.1 years, which was stronger in the AMO and weaker in the PDO. This peak was not evident at a statistically significant level in the land temperature average, in the ENSO, or even in other ocean indices that were examined. Using the Monte Carlo background estimation, it was also concluded that the multiple different global temperature frequencies that were observed through spectral analysis done by other groups were not statistically significant. A correlation is not always considered causal. The association between Atlantic Ocean surface temperature fluctuations and global land temperatures may indicate that these temperature variations are responding to similar sources of natural occurrences. Since 1975, the AMO has shown a steady rise in temperatures from minus 0.35 degrees Celsius to plus 0.2 degrees Celsius, which is a change of 0.55 degrees Celsius. At the same time, the average land temperature increased about 0.8 degrees Celsius. These large temperature changes may be in response to a common element such as greenhouse gases. There is a chance, however, that some of these land warming effects are a direct response to changes in the AMO region. There is some speculation as to what may be causing these variable temperature changes. If the long-term AMO changes are being led by greenhouse gases, then the AMO region could be used as a positive feedback to indicate effects those gases are forcing over land. Alternatively, some of the long-term AMO changes may be caused by other natural elements such as fluctuations in the thermohaline flow. If this is true, then the humanity factor of global warming may be somewhat overestimated. In conclusion, this analysis shows that strong decadal variations observed in the average land surface temperature records are more strongly correlated with similar fluctuations observed in the AMO index as opposed to the ENSO index. This correlation indicates that the AMO may play an important role in the influence of the ENSO on world climate.